course, this is referring to some kind of a limit here. So I'll just put an x here. And some, it can be any kind of limit. Any kind of limit, you get this. And then what is this? This guy is 0. Obviously, this guy is 0. And then times this guy, question mark, we don't know. The question is, can you conclude that this equals to 0? Can you conclude that this equals to 0? No? Yes or no? Well, if you put that equal to 0, then let me tell you, you know what? That is your score right there. Okay? So this is an incorrect argument. Okay? So the question is, in this case, let me put a question mark. Let me put a question mark here. There's a big question mark. Okay? So the question mark is this right here. Is big question mark right here.
Professor, I had a question about the first example.
Yes.
You could check that it goes to infinity by plugging in numbers, any number bigger than 0, right?
Right. When the limit is infinity, what that really means is as x gets closer and closer to that number on the limit, then that whole thing will get bigger and bigger. That's what that infinity means. So if you plug in like, let's say x equals 0.00001, then you know that number will be a huge number. Oh, that will, if you plug in x equals 0.001, that will be almost 1,000. If you plug in x equals 1 over a million, x equals 0.000001, then that will be almost like 300,000. So you can see, you can check it on your own that in this case, the whole thing will not go to 0. And as you can see, this denominator has x, and then we have another sine x, which is also behaving like an x. So the entire denominator is actually approaching 0 much faster than the numerator 0. That is, if you actually create a chart, x, and then create what? 3x. So let's say here we create a chart. So let me create a chart. So let's say the chart looks like this, x, and then versus 3x, and then 3 times x times 3 times x times the sine x. So let's say if you have this, and if we create a chart here, then we create a chart like this. Who do you think is going to approach? Who do you think is going to approach 0 factor? Like this. So this guy's approaching 0. This guy's approaching 0 too. Yeah, we know that. That's not a problem. But who do you think is going to approach 0 factor? When x equals, let's say when x equals 0.01, you know what this denominator, numerator, what this 3x sine x is going to be? Well, that will be almost, let me put almost here, almost 3 times, and then times 0.01, and then times 0.01. It will be almost like this. So this is going to be much smaller. So how big is this? That will be about 0. That will be about 0. What? 0.0003. So what I'm trying to say is we know that both of them are going to 0. But what I'm saying is this guy right here is approaching 0 much faster. In other words, the denominator is a strong 0. The numerator is a weak 0. This is a weak guy. Weak. Bottom is a strong one. So in that case, the bottom 0 is going to take over. How much time? How faster is the denominator going to 0 faster? About roughly infinite time. So therefore, when these two guys compete, the denominator is going to take over. The denominator is going to approach much faster. The ratio is in fact heading to infinity. So what I'm trying to say is one guy is heading to 0, and the other guy is we don't know. So let me erase this again. So let me erase this. A lot of students are still applying this rule. We have a limit here, and then you split as a product, and the first guy is heading to 0. And then in that case, some of you are so happy that you got a 0, because the second factor, we don't care, right? But if that's the case, the limit of anything is 0. Why? Look at this. Now look at this argument right here. Look at this argument. So we have limit of f of x with some kind of a limit. So what will that be? So we can say that f of x is equal to x times f of x over x, and then split the limit as a product, and then this guy's heading to 0. And then this guy's heading to 0. And now here we get some nonsense. What is the nonsense? The nonsense is that limit of anything is 0. So it doesn't make sense, does it? So do you want to say that limit of anything is 0? No, that can't be. That's impossible. But that's what it is, right? So if this is 0, so just because, especially when you convert this to product, it's split as a product of limits, and the first guy is 0 or anything is 0, then you have to check the other guy. Note that this guy right here in this case is what? Heading to plus infinity. So we have a competition here. And therefore the 0 does not make sense. The split does not work. The split does not work. Thus, let me say this. If your answer, if the prompt to your limit is 0, then think twice. As a math teacher, I try everything so that no students are going to get lucky. All right? So the teachers tend to avoid problems where the answer to the limit is 0 or infinity. We don't like those problems too much. Although sometimes it could show up. If the limit is 0, make sure that the limit is 0. But be careful. Again, generally, teachers do not like to put problems with whose limit is 0. If students make a mistake and they can still get a 0. There's a good chance. There's a good chance that student will make a mistake and get a 0. When students make a mistake, usually the answer is 0 or infinity. So that's why we want to avoid those kind of answers. And if it's 0, make sure the argument works, especially this limit of product, splitting the limit as a product of two limits. This is very common. And then one guy 0. And then what? And then 0 right there. Oh, it's a very common argument. I see this mistake on every quiz, every test. And I'm sure that on this test also, somebody might be making this mistake also. So be careful. When you split as a product and one guy 0, then you have to still check the other guy. Okay, you have to check the other guy. You have to check the other guy that the other guy is not heading to infinity or minus infinity. If it does, then we have a competition. It doesn't work. Like I said, he looked at this argument right here. If your argument works, then the limit of anything is 0. And that doesn't make sense. See? Limit of anything? And so one guy is heading to 0, the other guy, it doesn't matter, 0. Well, there's no limit. Then we don't even have to study limits because everything will be 0 if what you're saying is right. Okay? So watch out. So 0, if the answer is 0, think twice. Although that may be true, but be careful. Okay? Many times it is not. Again, teachers don't like to give you problems where the answer to limit is 0. And the teachers generally don't like it. And personally, I don't like it either. But once in a while, you will see a problem where the limit is 0. So I'm not saying that I won't give you a problem whose limit is 0, but think twice. Be more careful. Or any questions on these limits here? Now, this limit is not just for the limit of products, not the splitting the limit into a product, but this is for any split. Any split, the sum, difference, or product, or quotient, or exponential. If you apply limits separately, then what? Then you have to be careful. Now, if you split the limit, and any one of the split limits is anywhere between 0 and infinity. Let's say we have a limit. Let's say here, let me write this down. If you have a split here, and any limit right here, any limit is between 0 and what? 0 and infinity, then you can split. If it's not 0, okay, so let me say this. Let me write this down here. Undo. Okay, so if after the split, if any part of limit is a number between 0 and infinity, that is not 0 and not infinity, not infinite. In mathematical, we call what we call bounded. Bounded. Then the split is valid. If you split the limit in any way, and one of the limit happens to be a number which is not 0 and not infinity, like such as like any number like 3 or 5 or 0.1 or half or 10 or 100, then the split is okay. The best thing we get is if you have a number, then that is always valid. So if you split the limit and then any part of the limit is either a number anywhere between 0 to infinity, but not 0 to infinity. Actually, it could be a negative number too. It could be -5 or -10. It could be -half, but it is not 0 and infinity. Basically, when you look at all these indeterminate forms, 0 and the infinity are the ones which are causing this indeterminate. That's what makes it indeterminate. 0 and the infinity. If something is not infinity, not infinity or minus infinity or 0 plus or 0 minus or 0, then you can split the limits usually. But then there are also cases where the limit is an oscillation, so it's not heading to infinity. So there are some unusual real cases here, but generally that is the case. All right, generally that is the case. But especially when one part of the limit is 0, watch out. Watch out. You know what? When one guy is 0, and then you just proceed onto this limit here, you proceed, the chances are you'll probably make a mistake. All right? If any one of these guys happen that, if you get like 0 plus, if you get 0 plus 0, then that is of course 0. Or, you know what? But again, if it's infinity times infinity, then that is infinity. But anything other than that, like 0 times something is 0? No, not yet. Okay, not yet. So not yet. So let me see. Not yet. Must study further. It may be 0, or it may not be 0. It's an indeterminate form. You have to study further. Indeterminate form means it is not decided. Cannot be decided. That's what indeterminate form means. We don't know what's possible. Many results are possible. Okay? So one guy 0, well, slow down here, slow down. Don't be too quick. Especially this product form is very common. Or any question on any of these limits here? Okay, so let me now save this, and now I'm going to clear all this. So let's see, I have here, and so where are our files? Yeah, I did yesterday. I did upload the answer to the quiz 5, the quiz which you took yesterday. And here is the file. Oops, where's my? Yeah, but I did not show you all the work. I think I just gave you the answers. Oh, error. Oops, there's an error here. Something wrong with this file. Gee, something wrong with my file here. This is taking a lot of time. I think the computer's slow. Oh yeah, there we go. So that's quiz 5, and the answer comes up with this right here. And I'm not showing you work here, but anyway, if you know what, after class, if somebody wants me to show me this work, if any of you have any questions, then you can pick your V or W, and then I will do that problem for you, all right? And the V and the W, you don't have to pick yours. When you ask me the question, you can pick any V and any W, and then for that V and W, I can do the problem, okay? Otherwise, there's too many V's and U's here. The solution actually looks much more complicated than what your individual solutions look like. Because I have to constantly copy B plus 2, W plus 3, and so on. And so I didn't want to do that here. So, anyway, the final answer comes up with this right here. It's, so that's the final answer. And the final answer, it does not depend on what the V is. It only depends on what the W is. Okay? So, by the way, the W is the last digit. Oh, by the way, whether the W is the last digit or V is the second to last digit, always check this. because the W and the V, or I can use any other letter, K or M or P or whatever, but whatever it is, always be careful. This W and V is these are no secrets here, so these things will change. On one test, W could be the last letter, and then on the next test, V is the last letter, but I try to be consistent within the test. If V is the last letter, last digit to your SMCID, then I try to make V equal to the last digit of your SMCID throughout the entire test. Okay? But every test is different. Sometimes I use the letter K, let K be the last digit or something, and then let P be the second to last digit, or the penultimate digit. Okay, so anyway, I'll change here. So please watch out, be careful. All right? So example number 1 was that, and then number 2, horizontal lines. Most of you got the horizontal line correctly and the tangent points correctly, but some of you couldn't figure out what the normal line was. A normal line is just a vertical line. So in this case, x equals plus or minus square root of 2. So in this case, we have 2. If you have a plus, then plus, 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 that you all take all the plus positive signs, you take the top signs, and then if you take all the bottom signs, that will be another choice. So in this case, we can conveniently write this plus minus here throughout, and so we will have 2 solutions. Again, sometimes instead of plus minus, you will see the notation minus plus. So if I write x equals minus plus, does that mean that is a different answer? Let me see. Where's my I want to write this here. Okay, so I have this. Where's my thing? Notes. Where's my notes? Okay, my notes are gone. How do I make my notes show up? Sorry. So, okay, what is this? No, what is this? Notes. What? I don't know. Suddenly my notes, the board is up. Where do I go to start writing notes? You know what? I don't know what happened here, but I don't know where to click to start notes. What is it? Usually shows up here. Okay, anyway, you know what? So if you look at number 2, you can see that this guy's it still bothers me. I want to write notes, but I don't know where to go. So here, you know what? I'm not sure where to go. Usually the bottom, it shows up, but again, it's not showing up. This one here, share screen. If I do this, that's a whiteboard. Okay, the whiteboard that shows up. Okay, now if I erase the whiteboard, now let's see. This one I share screen. This is the screen. Now I see it. Now okay, there we go. Okay, so now x is equal to plus or minus square root of 2. If I write x is equal to minus plus square root of 2, does that mean the same thing? If I write minus plus square root of 2 like this, then will that mean the same thing? And the answer is no. What this means is if I take plus here, then I take all the top signs, that will be one set, and then I take all the bottom signs, that will be another set. Okay, so here plus minus, here none of them. I cannot change this plus minus into a minus plus. If I put minus plus here, that will change the meaning. All right. So anyway, besides that, I think everything's clear. So that was from number 2, and then number 3. Yes, number 3. I'm showing you all the work here, and yeah. So I mean the answer looks much more complicated than what it should because there's a bunch of these V's and W's here. Now let me just make a general comment here. When you have this factor here, many of you multiply this out. You multiply it out to 3, and you wrote 2 terms, but that is not required. Generally, If you give me the expanded form of an expression, I'll accept that. But especially if you give me the factor form, I will accept that as well. In fact, I do prefer the factor form. So if your answer is in factor form, there is especially no need for you to multiply out. Multiplying out is not required. In fact, I do prefer the factor form. Generally in math, we like the factor form rather than the expanded form. But I will accept both, but especially factor form, I accept that. All right? So again, no need to waste time to expand any of them if it's a factor form. All right, and then of course I put a note here. So anyway, that's it. And this is the solution to example 5, quiz 5. And again, I only wrote down the answers here. I read actually for number 2 and number 3, that is the full solution. Number 1, I didn't write the solution here. So this is solution only. And so there's also also the solution to quiz 4. I posted it also. And the solution to the midterms and the quizzes will always be at the very top of the file. So you will see the answer to the midterms, and then after that, you will see the answer to quizzes. And then quiz 4 solution, is there too. So you can look it up if you have any questions. But many of them, I will just give you answers because I do not want to give you the general solution. The general solution with a bunch of V's and W's and all these parameters looks much more complicated than your individual solution, and therefore I didn't want to confuse you too much. Okay, so that's that. So now what I would like to do is now let's move on here, section 2.8. Section 2.8, let's do it. Section 2.8. So this is something which I couldn't cover last time. So once again, on today's test, there will be no related rates. So this related rates will be covered on future quizzes and also will be covered on future quiz and tests. So midterm 3 will cover this section, and all the quizzes which I might give you will cover this one, of course. Okay. Of course, today we have a test, so there's no quiz, there's no separate quiz. But I might give you a quiz on related rates tomorrow. Okay. So or any day after. Okay, so let me just do this here. And then after this, I'll have a little bit of time if you have any questions, okay? So we'll see. So why don't I start with section 2.8 here? Okay, so this is section notes 2.8. Clear? And so we have done example 1 and 2 yesterday. So now let's move on to example 3 and example 4. Let's do it. Okay, example 3. Okay, let there be a rectangle where length is increasing at the rate of 5 inches per hour and width is decreasing at the rate of 3 inches per hour. At what rate is the area changing when length is 20 inches and width is 8 inches? Is the area increasing or decreasing? Okay, so let's see what we have here. So we have a rectangle which is 8 by 20. So you know what? Let me make an observation here. So this will be an observation. So annotate. So this will be an observation. So let me make an observation here. Observation. So observation. What is observation? Observation is basically just observing. Observing is a step for us to understand the problem. Observation is not required, nor is it part of the official solution. So whenever you have a problem like this and you don't really understand it, then I want you to make an observation. An observation sometimes includes graphing as well. But here, there is no graph here. So let's try to understand this problem. So once again, when I write observation, what is that? Observation is a step for us to understand the problem. Because on all math problems, understanding the problem is the key step. So it is not part of the official solution, and you don't have to write observation. But if you write something on observation, then I might still give you some credit. But of course, this is not the official solution. Therefore, there won't be that much credit. But observation is mainly to help us understand the problem. So what is the step here? To help us with observation. I mean, to understand the problem. Is that clear? This is again not part of the official solution. official solution. But this is something I recommend all of you to do this, because many students do not understand what the problem is, and you just jump in, especially water problems. So you have to make an observation. So here, let me make an observation, and so let's do it. So here is this here. So what is this? So we have a rectangle here. So rectangle, and this is now what? 8 by, what is this? 20 by 8. Okay, so we have a rectangle which is 20 by 8. Okay, so now we have a rectangle 20 by 8. Now, what is this here? So let's see. This is the length. So in this case, we can either we can let length be the length be either side. So in this case, how about if I let this side be L, and this side be width? Again, it does not matter. Mathematically, there is no difference between length and width. We can actually call the short side length and the width. Again, it's not that the longer side is length and the shorter side is width. Sometimes the length and width can change then. The longer side can get shorter, so we cannot define that way. So either side is length or width, so it really doesn't matter which one is length and width. And so now let's look at the problem here. Rectangle where the length is increasing, so the length is increasing. So the length is increasing. So what we can say is that the length is increasing. So the length is increasing, that the length is going to be, let's say 1 hour later, the length is going to be like this, longer, but the width is actually going to get shorter, so like this. And then on this side, let's put a length is now shorter, and this is actually taller like this. So let's say we have this. So now what I'm trying to say is, this is the width and the length, and this is the length and the width, and this is the length and the width. But now this is different times. So in this case, why do I say that the time is 0 here? So in this case, let's say the time is 0. So this one here, let's say that the time is 0. So t is equal to, in this case, 0 hour. And then the second one, the one on the right, why don't we say that this is the when t is equal to what? 1 hour. When t is equal to 1 hour. And then this one here, the rectangle on the left, this is the rectangle, this is how the rectangle looks like when t is equal to minus 1 hour. And again, that's how the rectangle looks like when t is equal to -1. So for some kind of a time scale, okay, we have this. And then this is how it goes. Now, at time t equals 0, what is the length? Length is actually equal to what? Is 20. So 20 and 8. Okay, so let me write that down. So this side is equal to 20. So this is 20, and this side is 8. And the length is 8. This is 8. Okay, so let me put length, width is equal to 8. And then now the length is increasing at the rate of 5 inches per hour, right? So this is now 25. And used to be 15 over here, 1 hour before. And then how about the width? Width is 8. And the width is what? It's decreased at the rate of 3. So that means this decreasing, so this is now 5. And this guy is actually what? This guy is actually 11. So in this case, what is the area? In this case, area is equal to width times length is equal to 165. That is 15 times 11. And then at t equals 0, what is the area? Area is equal to 20 times 8, which is 160. And then at t equals 1, what is that? Area is equal to 125. So at x, when t is equal to 0, is the area increase or decreasing? Again, when at t equals 0, at that instant, is the area increasing or decreasing? Now, when you look at this from 165 to 160 to 125, it looks like it is decreasing, but this is not conclusive. It looks decreasing. But again, who knows? Maybe it goes up to, maybe it goes from 165 down to, let's say, 150, and then from 150 it came up to 160. So at that distance, it may be increasing or decreasing. So it's not conclusive. Again, it is not conclusive that at t equals 0, it is decreasing, although from t equals 1, -1 to t equals 0, it looks like it is decreasing, when t equals 0 to t equals 1, it looks like it is decreasing again. So it kind of looks like decreasing, so it looks decreasing. So in this case, at t equals 1, at t equals 0, at t equals hour, area looks, area is decreasing, decreasing, not conclusive though, not conclusive. So I'll just say inconclusive. Inconclusive. It's not, you cannot be sure. Because even then, again, it can go up and down and up and down. And at that instant, at t equals 0, it may be increasing. But in this case, generally, it kind of looks like it's decreasing, but we can kind of have a feel here, okay? So anyway, that's the question. So now we want to know is, we cannot just go from -1 to 0. If we do that, if we now, let's say, take, what is this here? This is now the change in area. So let me write this down here. So what is this? This is going to be change in area. So the change in area, the delta A, change in area per time, let's say per t, and this is the time from what? Between t is equal to from -1 to 0. So we can actually put a notation like this. Then this would mean the average rate of change, that is the change in area per change in time, between t equals -1 to 0. So if you do that, that will be, so how much did it change? From 165 to 160, that is -5. And then what happens from minus t, delta t, to -1 to 0, that is a +1. So the answer is actually equal to -5. -5, or not, -5 inch squared per hour. But that -5 inch squared per hour, that would be the average rate of change. That is not the instant rate of change. So in order to find the instant rate of change, what happens here? We have to what? Close the gap of the time to 0. Right now, there's time difference of 1 hour. So if, as long as there's like a certain time gap, that is not the instant, that's only the average rate of change. Okay, so now let's get to the solution. How do you get the solution here? So now let's get to the solution. This is how the solution. Okay, so how do you get the solution now? First of all, looks like this is a problem rectangle. So why don't we now draw a rectangle? So the rectangle can look like this. Okay, we have a rectangle like this. And then now, why don't we call this guy, why don't we call this guy L and W. This guy's L. This guy's W. And what is the question here? The question we have is the, area. So when you look at this question here, it says, at what rate is the area changing? So the question is about the area. And then what's the given condition? The given condition is that the length is changing at this rate, and the width is decreasing at this rate. So it looks like the given information is about the length and the width. So we now have A, N, L, and W. Okay, so these are the variables we need. Again, on word problems, don't just create all the variables you need. Don't just make up all the variables. Okay? We only want to create variables which we need. Okay, so here is, be careful here. Of course, these problems are not that complicated, so if you just call it L and W, there's no mistake. But don't just create any variables. Don't just create any variables. Just create variables. Just define variables. Just define variables. Just define variables we need. All right. So you see a picture and then you start writing formulas. Well, don't do that. We don't know whether we need the surface area or the volume or the perimeter. We don't know what we need, or sometimes we need the angle. If you look at example 4, we actually need the angle. So we don't know what variables we need. Okay? So the question is, just define variables we need. Don't just create any variables. So that will be the beginning of mistake. So in this case, we have that. Okay, so now what? So maybe I'll just, maybe I'll just undo this here. All right. So now what? So now the relationship between the first step is this. Now, the first thing is we have to get the equation which relates to variables. And that equation can be any equation which relates to variables. It can be any equation. And of course, among the equations we want the simplest one. So what is the relationship between the A and the L and the W? And that's not too hard. A is equal to LW. You know what? Let me just write L and W because I'm handwriting this here. So what I would like to do is let me just use the capital letter L here because the small L kind of looks like a 1, and I don't want to confuse you there. So let me just use the capital letter here. And the W, well, the capital letter and the small letter, they kind of look alike. So A is equal to LW. Now, note that this equation, A is equal to LW, has how many equations? How many equations do we have? Or how many variables? How many variables do you see on the equation A equals LW? Including the dependent variable as well as the independent variable. How many variables? 3 variables. 3 variables without t. I'll talk about the variable t. In this case, there is no t. So t is not one of the variables, and we have 3 variables. If we have 3 variables, how many conditions do you need then? Okay, we'll have, how many variables? We'll have 2 conditions. 2 conditions or 2 conditions or constraints. Okay, and then we'll have a question. So that's how it's going to look like. So this one here, let me call this the setup. Setup, and the setup is going to look like this. The setup is going to look like this. Now, what are the conditions here? Now we have the condition here. We have dl dt. dl dt. So what is dl dt? How is the length changing per time? So the dl dt is equal to what? The dl dt is equal to, what is this? Length is increasing at the rate of 5, so this is equal to 5. It's actually plus 5. The signs are significant. Therefore, this is 5 what? Inch per hour, if you will. Okay? So we want to be able to put the unit here. Is the unit required? Well, it is kind of required. Okay? I'm not going to be too picky here. This is not a science class, but you know what? Ultimately, all of you will be taking some science. So yes. So how about this? Let me change my mind. The units are required. Okay? So as of now, the units are required. And then now the other one is going to be W. So how fast is the W changing? With dW dt. And so how is the W changing with respect to time? And then it says here, with this decreasing at 3 inches per hour, so therefore this will be now what? Minus 3. Minus 3 inches per hour. And now, so we have 2 conditions. So by looking at the equation and counting how many variables we have without t, the number of conditions will always be one fewer than the number of variables. If you have 3 variables, then you need 2 conditions. 2 variables, you need 1 condition, and so on. Okay? And if you have 4 variables, then you need 3 conditions. That is, if you have a setup with no t. Okay? And then what is this here? Now the question is what? Question, find what? Find, what is find? Find what? Find dA dt. dA dt. Then what is the time condition we need? dA dt when what? When, and then time condition when L is equal to what? L is equal to, what is L? L is 20. And what? W is equal to 8. And of course, it's going to be inches. 1 inches and 8 inches. Okay, so this will be the setup. Any questions about the setup? Any question about the setup?
No.
So what I'll do is I'm going to erase all this. So I'm going to erase this for now, okay? And then I'm just going to use all the space. So now how do you actually solve this? To solve this, let's do it. Solve. How do you solve this? Well, we apply ddt to both sides. ddt to both sides. Apply. Okay, differentiate both sides by t. If we differentiate both sides by t, now this is what? What is this then? This is now dA dt. So we now have dA dt. So what we get is dA dt. So let's write it. So that will be dA dt. So dA dt, and then is equal to, the right side is now what? L and W. And of course, A and W and L, they're all changing by time. So they all depend on time. So dA dt is equal to, none of them are constants with respect to time. So now we have a product rule, dL dt. So this is dL dt. So this is dL dt. And then times W. And then plus F prime G. That will be L times, and then dL dt. dW dt, that is. So we now get this. So now, from here, what is it? We're trying to evaluate the dA dt. So the dA dt is not substituted, because that's what we are trying to look for. So that's the question. The question is dA dt. So the dA dt we copy, and all the other guys, all we have to do is what? Basically plug it in. So we have this times that, and then times that, and then times that. And I like to put these parentheses before I substitute. Okay, so what is 5? 5 is dL dt, this guy right here. What is minus 3? Minus 3 is dL dt, which is right here. And the time condition, W is equal to what? W is equal to 8, which is right here. What's L? L is 20, is right here. And by the way, this, so the setup is right here. This is the setup. Again, the setup will always be worth at least half of the problem. If the problem is worth 10 points, then the setup will be at least worth 5 points. At least 5 points. Sometimes more than 5 points. Sometimes 8 points. That is 8%. Sometimes even 9 points. 90% of the stuff. Sometimes I will only ask you for the setup and not solve the problem at all. The setup is a more important step. Setup could be 100%. So when you study for the section, spend all the time getting the setup. That's the first step. If you can't get the setup, then there's nothing left. So this is to spend all the time getting the setup. And this now I made a mistake here. Undo. The setup is actually including up to here. And this when, and then when, and then this right here, this is what I call the time condition. The time condition. And by the way, the time condition, when do you need? Time conditions used after, used on equations after differentiation. So this L equals 20 and W equals 8 will not be plugged into that equation A equals L times W. It is not plugged in there. The time condition is always used after we differentiate the equation. So once we differentiate, we get the equation like this. And then once it's differentiated on that equation, we will be using the time condition. So never plug these time conditions on the equation before differentiation. All right? Because a lot of students, they write this, and then they start plugging this L equals 20 and W equals 8 into the equation. And then if you do that, you get error is equal to 160, but that will be useless information. The fact that the error is equal to 160 is useless. Yeah, that's correct, but again, that information is not that useful. Okay? So now, let's finish up the problem here. Yeah, the finish up, that is, we are almost done. So basically, this is going to be what? Minus 60 plus 40, this is minus 20. So indeed, at that instant, what is happening? The error is actually decreasing. The sign is going to show. And sometimes when you do these kind of problems here, we don't know whether something is increasing or decreasing. We don't know. In this case, we check that t equals -1 and t equals 1, and so before and after, it looks like it is decreasing. Is the error decreasing? It kind of, but that at that instant at t equals 0, we are not sure. So this is inconclusive. It may or may not be increasing. So in this case, it turns out it is decreasing. So as you can see, it is kind of decreasing here. problem yet. Okay? Inconclusive means study harder, study further. That's what it means. Okay? All right, so this is it. Any questions on this? Now, this setup right here, this is what I call the standard setup. Let me call this the standard setup. So this one here, the standard setup. Standard setup. This standard setup is the setup you will see on most calculus textbooks, and in most calculus textbooks, they just teach you this way. And so if you do this, that's fine. And this is a fine method. I'm not saying that bad, but now I want to introduce another setup. And another setup is the setup by time. Okay, setup by time. Okay, so I'm going to do that. So now in this case, this is the standard setup. So now what I'm going to do is I'm going to now erase this. So that the answer came out be -20. Well, I didn't write the units. What is the unit to this -20? Can somebody tell me what the units are? -21. -20? Can somebody tell me the units of this -20?
Is it inches per hour?
Inches per hour? Well, almost. Not inch per hour. It's actually inch what? Inch square per hour. Why is that? Because if you look at this 5 here, what is the unit of this 5? This 5 is inch per hour. But then what is an 8? This 8 is actually what? 8 is actually inches. When you multiply the units here, you get inch square per hour. And then plus, and then what is 20? This 20 is inch per hour. And then -3 is actually inches. No, 20 is inch. And then -20 is, -3 is inch per hour. And so when you multiply these and then you add those, so of course when you add, the units don't change because you're not multiplying. So the answer is inches per hour. And besides, when you look at this is changing area per time. How much area is changing per time? And the unit of area is, of course, inch square. And the time unit in our case is hour. So the unit is inch square per hour. So it's important that you know these units here. And the answer is yes. You should know. Yes. So I would say, but you don't need to put the units on every single the middle step here. If you just write the units one time at the end, that will be good enough. So write the units one time at the end. No need to write the units in the middle. Of course, as long as all the units are clear. You should have an hour here and a second there and a day over here somewhere. They just have to make all the time units uniform. And all the length units have to be uniform too. So here everybody is using on the entire problem, all the units in length are inches. Inch, all the inches throughout. So all the length units or the distance units must be uniform. And all the time units must be uniform as well. In this case, throughout the entire problem, the unit of time is hours. Okay, so much on that. This is a standard solution. Now what I'd like to do is, I would now like to introduce the second type of solution, that is set up by time. Set up by time. Let's see what we have here. So I'm going to erase this. I'm going to erase everything here, but I'm not going to. I'm going to also erase the setup here. Setup. Okay, setup here. And let me also what? Oh, wait, you know what? Did I save the screen? Did I save the screen? I don't know whether I saved the screen. I don't think I saved the screen. I guess I have to do all the way here. Let me see. Sorry about this. I will have to save the screen first. Okay, so this is the screen. Yeah. So let me now save the screen. Almost forgot. So now I'm going to redo. Oh, I can redo this. So there we go. I don't have to erase it again. So let me just redo this, and then so this is how it's going to look like. Okay, so now what I'm going to now is I'm now going to introduce another setup. And on the test, you can do either setup. By the way, this setup by time can be done on any example. Any example which involves time, there's always this setup too. So now this time I'm going to give you another setup. This is now setup 2. Setup 2 are also setup. This is setup by time. Setup, okay, how about this setup? This is setup by time. Time t. By time t. Okay. Okay, first of all, what is the equation here? What is W? What is W here? W is what? W is equal to here, set up by time. So in this case, we want to express everything by time. So what we have is what is L? So let's look at L. L is equal to when you put the L here, L is going from 15 to 20 to 25. Looks like L is equal to 5t plus 20. 5t plus 20. 5t plus 20, not tt. So L is equal to 5t plus 20. So when t equals 0, L is equal to 20. When t equals 1, it's L equals 25. When t equals negative 1, it is 15. So there you go, good. And then now what's the W? W is equal to what? W is equal to my decrease of 3, so that will be minus 3t. And then plus what? Plus 8. So note that in this case, when t is equal to 0, W equals 8. When t equals 1, W is equal to 5. When t equals negative 1, W equals 11. So the W is actually decreasing by 3. Okay, so now what we need is the A. A is equal to what? 5t and then plus 20. And then times minus 3t and then what? Minus 3t plus 8. And now, what do you want? What is the question here? The question is this. The question is, find what? Find dAdt. So let me write dAdt. So this is going to be what? This is going to be find dAdt. So dA dt, and let me put a bar here. Find dAdt when what? When time t is equal to 0 hours. In this case, these equations L and the W are set up in such a way that the question when t is equal to when L is equal to 20 and with W is equal to 8 actually happens when t equals to 0. So everything must be in time units here. So in this case, now this part right here, this part is kind of a supporting data for the setup, but this is the ultimate setup. This is what I need to see. This is called the setup by time. Setup by time. So when you set up by time, as you can see, there is no condition. There's no condition. Everything is kind of built into this right here. So if you do this here, now if you set up this way, then how do we, by the way, I need to erase this part too. This part is we got minus 20 here. We did get minus 20 at the end, right? So let me just erase all this, and then let me just leave it that way. So if you now do it this way, if you set up this way, the question is, are we going to get the same answer? Yes, hopefully we will. So in this case, what we get is we get this. So now what I'm going to do is, let's now solve this. So how to solve this? Now we apply ddt to both sides. Apply ddt. So we are going to differentiate both sides by t. So if you do that, what we get is we get dAdt. dAdt. And then dAdt, what is that equal to? dAdt is equal to this. And note that this guy is actually a product. So should we just apply the product rule, or should we just multiply this out and then differentiate the quadratic function? Yeah, it's only a quadratic function. If you want, you can multiply this out. That might be easier. Or you can just use a product rule. If you apply product rule, then we get f prime is f prime g 5 times what? Minus 3t, and then plus 8. So let me write this down. How about this? I think I can type it in. So let me just type this in. If you take the derivative, this is what we get. We get 5 times. So we get 5 times. So 5 times what? Minus 3t plus 8. Then plus f prime g, 5t plus 20. And then times the derivative of the second factor, which is minus 3. You get this. And so what happens when t equals 0? So now we have to evaluate when t equals 0. So what is that? That will be this. So now from here on, What is dAdt? So dAdt. So how is this dAdt? How is the area changing when t is equal to 0? So t dt. And then at this point, we now going to plug in t is equal to 0. So when you plug in t equals 0, what do you get? Yes, we do get what? T equals 0 here, we get 40. 5 times what? 5 times 8. Okay, so you know what? Let me just, erase this. I'll just type in all the numbers we get. So what we get is we get 5 times 4. So we get 5 times 8. 5 times 8, and then plus, and then we get 20, and then times, and then it looks like we get minus 3. So if you add up all that, 40 minus 60, that will be minus 20. Minus 20, and the unit will be what? Inch square per hour again. So inch square per hour. So we get inch square per hour. Again, this kind of setup by time is always possible whenever there's a time involved. Does this problem involve time? Yes, it does. And in fact, majority of the problems you see on related rates is actually involving time. So for any word problem which involves time, there is always a setup by the time. But many textbooks and many teachers, they don't show you this way because the standard setup is good enough. You don't have to really know this. And in particular, this setup is not really more advantage in any way. Okay, so it's not really a better solution. So there's not much. Okay, so I mean, but I think it is. I think it is good if you can understand this in both setups. So my stance is the more methods you know, the better you will be. Okay, so you have better viewpoints. So the more ways you know, the better it is. That's my philosophy. So as a student, learn all the different ways possible. So you cannot do both ways on every problem. So what I recommend you to do is this. On one problem, do the standard setup. On the next problem, do the setup by time. And then so try to alternate different methods on different problems. Again, you have no time to spend, unless you want to check it. If you want to check and you want to verify, then you can do both methods in one problem. But of course, the other method is not so hard either. So once you get the hang of it, then that's it. Note that this setup by time is possible for any problem which involves time. So that means if you look at example 1 and 2, example 1 and 2 didn't have that time involved. Was there time there? Anyway, we get time. So how about, let me save this and then clear. Now, if I, let's say, go up here, actually example 2 is involves time. So for example 2, there's a setup by time. And example 1, there's also time too. So there's a time setup as well. And then if you look at example 4, example 4 is also a time, also has a setup by time as well. And then if you look at example 5 in the bottom, yes, also has time too. So all of the problems up to example 1 through example 5, and also most of the examples on these related rate problems involve time. About 90% or 95%. But once in a while, you will see problems where you're not going to have a time in the problem. Okay? So but problems which involve time, there is always a setup by time. And then the time condition is usually made at t is equal to 0. Although it doesn't have to be t equals 0. It depends on how you set up the time frame. All right? Do you want that the time in question be t equals 0? Or do you want that t to be 1 or 2? Or do you want 1 hour? Or do you want 1 minute? So there's the way you set up the time units, okay? The time scale. All right, now let's look at example 4. Did any of you have any questions on example 3? No questions? Thoughts? Okay, let's do example 4 then. In example 4, let's say there be an isosceles triangle where two equal sides are 4 inches. Let the angle theta be between the two equal sides, which increase of there are all kinds of grammatical mistakes here. Let's see, let the angle theta be between the two equal sides. Well, increasing, which increase at the rate of 30 degrees per minute. Part A, how fast is the length of the other side increasing when theta is 60 degrees? Part B, how fast is the area increasing or decreasing when theta is equal to 135 degrees? Now in part B, I will not say whether it's increasing or decreasing. I will say rather than increasing, decreasing, I will just say what? I'm not going to ask you whether it's increase, decreasing. I will probably use which word? I'll use the word. How is the word? Changing. So if I use the word changing, that obviously means I'm not telling you whether it's increasing or decreasing. So that is the word which I actually like to use more. Okay? So I will not say increase, decrease. I would rather say how fast the air is changing when theta is 135 degrees. So I'm not telling you whether it's increasing or decreasing. So you have to show that too as part of the answer. All right? Okay, so example 4, I like this question. Why? Because this problem involves angles. And not only angles, this problem involves some trigonometry, some formulas on triangles. So the question is, do you all know everything about these triangles? So this is about triangles. So now, before we continue, so it looks like we need some triangles here. So let's say we have a triangle. Let's say call the three sides, A, B, C. And this problem involves what? The other side, the length of the other side, okay? So if you know two sides A and B, what is the length of the other side? So this is now the cosine law. C squared is equal to what? C squared is equal to, everybody knows this? C squared is A squared, and then plus what? Plus B squared minus 2AB. Let me see. Minus 2AB. Okay, let me type this in. C squared is equal to A squared minus B squared minus 2AB, and then what? Cosine of cosine C. So let me write cosine C in parentheses there. So cosine C. So this is the what? This is called the cosine law. Either it is called the cosine law or it could be called cosine second law. Okay? But anyway, cosine law in general. This is the formula on triangles. Okay, so and then by the way, this C right here. So let me be careful here on what is this here? Eraser. Let me erase the C here. And so this C right here, this C is actually small c because this is small c, tiny c. And oops, that tiny c, I should make it tiny c. Is this C. And the big C is actually right here. The big C is over here. The angle is going by the capital letters, A, B, C. And this is called a cosine law. And now second is about the area. Area, okay, so what about the area? Area of this is the area, so let's say area. Area, what is the area of this triangle? Area is equal to half AB sine C. AB sine C. Of course, all formulas on trigonometry, all formulas on triangles, they are symmetric. If something is true for A, then the same thing is true for B and same thing for C. So if C squared is equal to A squared plus B squared minus 2AB cosine C, then what can you say about A? We have the formula for A as well? Yes, we do. We can say A squared is equal to what? B squared, and then what? P plus C squared, and then what? Minus 2BC, and then what? BC cosine A. So all the formulas are symmetric among all the variables. If something is true for one variable, then variables can rotate. Then we have this too. And the area formulas too. If area is equal to half times AB sine C, then of course this is the same thing as half times AC of BC cos DC, and then sine A. And of course this is BC sine A, not cosine A. The sine A, and this is of course also equal to half times what? Half times AC sine B. AC sine B, okay, like this. It rotates. So when you say area is equal to half AB sine C, of course the AB can be any two sides. So that's why we can rotate. Okay, any two sides. This means A and B could be any two sides. Right, so we need that. And what else do we have to know? Yeah, that's right. These theta, these units right here, the 60 degrees and 135 degrees, they have to be converted to radian units. All angles must be converted to radian units. So let me write this down. Start. All angles must be converted to radian units. So you don't know why? So in this case, one is 135 degrees. One is 135 degrees. 135 degrees is what? 135 is what? 135 is what radian? Oh, that was 3 pi over 3 pi over 4 radian. 3 pi over 4 radian. 3 pi over 4 radian units. So let me call this radian. So this is the groundwork. I like to do all the groundwork before we actually get to the solution. And so what is this 60 degrees? 60 degrees is what? This one should be easy. 60 degrees what? Is pi over 3. It's pi over 3 radian. The pi radian is 1 over 8. So please make sure that you have this. Okay, so now we have this. So now we are ready to do part A. So we have done all the groundwork. Let's say part A. Okay, let there be an isosceles triangle where two equal sides are 4 inches. So we have a triangle here. Let me use triangle. And then it says here this side is 4, and this side is 4. And the two equal sides. And the middle angle here, why don't we the middle angle is actually called theta. So looks like we have to call this guy theta. I think maybe I should have called this guy A so that I can type it in. Theta, I cannot type it in, right? So it's a little inconvenient here. So, okay, anyway, we have this. Okay, so now what is the question here? Well, how fast the length of the other side changing? So that means this side right here. This side is L. And what we want to know is when theta is increasing at pi over 3 radians per minute, how fast? Increasing at theta. How fast when theta is pi over 3? Okay, so we want to know how fast as the theta is what? As theta is increasing at 30 degrees per minute, we want to know how fast area is changing. So when theta is changing, of course the area is changing, and also the length L is changing as well. So part A, how fast is the L changing, and part B, how fast the area is changing. And now here, 30 degrees per minute, 30 degrees per minute, we have to change that one too. 30 degrees is pi over 6 radians. This guy is pi over 6 radians. Pi over 6 radians. This is radians per minute in this case. In this case, what? Radians per minute. Oops. Capital letters here. Radians per minute. So first, let's set up the equation. In this case, that's the diagram right there. So the given information is about the 4 there. That 4 is always, it's fixed. Now, the given information is that the angle in the middle is increased at 60 degrees per minute. And we want to know how L is changing. So what we want to do is, the first part A, what we need? We need to have a relation between the theta and the L. Any relation between theta and L will do. So can you tell me now, any relation must find the relation between what? So here, must find any relation between what? Between L and theta. Now this is hard because I cannot type the L and theta. So let me say L and theta. Why L and theta? Because L is about the question and theta is about the given condition. We only create variables which we need. Is that clear? Again, we only create variables which we need. And the variables must be created either from the question, either from what is asking the question, or what is being given on the question. So L, why do we need L? Because the question about the L. How fast is the length changing? Why theta? Because the theta is changing at 30 degrees per minute. So that's why we need theta. So the variable source is only from the question or from the given condition, nowhere else. So do not automatically create any variables here. Okay, so don't just create any variables. So we need a relation between L and theta. Now, what kind of relation do we need here? Not any relation. Any relation, any equation which relates L and theta will do. So, what do you think is a good relation? How about this? L squared is equal to 4 squared, and then plus 4 squared, plus 4 squared, plus 4 squared, plus 4 squared, and then minus, how about 2 times, minus 2 times, minus 2 times 4 times 4, and then times what? Times cosine what? Cosine theta. Cosine theta? Yes, cosine theta. So we have this. So do you think that is a good relation? Class, do you like this relation between theta and L? What do you think? We can have that relation. But this is not the only way we can set up a relation. Actually, there's a better relation. You know what that is? So this is an isosceles triangle. So what we do is, let's draw half of this triangle. If we draw half of this triangle, then I'm going to draw half of the triangle right here, and then this is now a right triangle. And you know, the good thing about this isosceles triangle is that when we cut into 2 equal pieces like this, 2 equal congruent pieces, then the half of that isosceles triangle is a right triangle. And of course, the right triangle is the best triangle we know. That's the triangle we like the most. So what I like to do is, how about this? Let me draw this a little bit bigger. I need to draw something. So let me now do this. I'm going to draw a triangle which is bigger, which is actually half of the triangle. So this angle right here, I'm not going to create another variable. I'm going to call this guy theta over 2. Theta over 2. I'm keeping the theta. So this is now theta over 2, because this is exactly half of it. And then this bottom side right here, this is actually L over 2. L over 2. And this is actually right angle, right here. And this is theta over 2. And this side is 4. So now if you look at this right triangle here, what do you see? We see a 4, we see L over 2, so what we do see is that we see this angle right here. We see this angle, and we have this side is 4, and this side is L over 2, and this is the angle, which is theta over 2. So in this case, what trig function is going to relate the 4 and the L over 2? So let's say cosine, we can use sine. What is sine of theta? Let me write this in red now. What is sine of theta over 2? Can you tell me what sine of theta over 2 is? Can you tell me what sine of theta over 2 is in that diagram there? What is sine of theta over 2? And of course, this is a right angle. Can anybody tell me what sine of theta over 2 is? What is sine theta over 2? Can you tell me? Class, are you all there?
Yes.
Okay. What is sine theta over 2? Using the trig definition of trigonometry, a trig definition of sine. Sine theta over 2 is what? Is the opposite over hypotenuse. So this is L over 2, and then over 4, but I'm not going to put over 4, I'm just going to put a 4 here. So L over 4, L over 2 over 4. So that's L over 4, L over 2, and then over 4. I just put a 4 there. So this is actually L over 8. This is L over 8. Oh, get this. So now, this can be the equation right here. Now this is also the equation which relates the L and the theta. So let me call this what? Setup 1. Setup equation 1. This guy is setup equation 2. Setup equation. How about setup 2? Setup 2 equation. This one here, let me call this guy setup 1 equation. This is a different setup. It's not that you need both equations, you only need one equation. Eraser, let me erase this part. This is, let me call this guy setup 1 equation. set up 1 equation. So take your pick. Which equation looks easy to you? So when you have to find an equation which relates L and the theta between the variables, we just need 1 equation. Any relation will do. So this relation, fine. This setup involving the right triangle, yeah, that will have a theta there, and L there. That relates L and the theta. And if you look at the second equation here, that also relates L and the theta, and nothing else. See? So either equation can be used in this case. In this case, which one looks better? The first one. So you can actually go by this right here. Set of equations is this. If you go by this one here, then what? Now the set of equations has 2 variables and there's no time. There's no time t. Can you have a time setup too? Yes, we can. This one has time too. We can have a setup by time as well. So this is setup 1, setup 2, and we can have another setup. I can write it down here. Maybe you should rate it when you study this setup. How about setup 3? How about setup by time? By time. By time, and then actually you can either set up by time using equation 1 or equation 2. So actually there's setup 3, but there's also setup 4. There are actually many ways to set this up. Okay. So anyway, we have this. And so now what is the condition here? The condition is that. The condition is what? The condition is that. What condition is that? What is this here? D theta dt. So we have d theta dt. D theta dt. D theta dt is equal to pi over 6. D theta dt is equal to pi over 6. Pi over 6 radians per minute. And the unit is going to be radians. Let me just write this the right unit form too. So this will be radians per minute. Per minute. Per minute. Here is radians per minute. I changed this from degrees to radians. And then now the other time minutes. Do we have? We have no other time. We have only one condition here. There we go. And then what is the question now? The question is to find. Let me write this in red. Find what? Find what is it? Find dl dt. Find dl dt. So find dl dt. You know what? Let me just write this in fraction. dl dt. dl dt. I'm using capital letters because small letter kind of looks like a 1. So I cannot use the small letter there when I'm typing. Okay, so this is basic dl dt. Should actually be the same letter. So you know what? Let me just overwrite this as small l. dl dt, and then what is the time condition? The time condition was what? I'm going when. Oh, and then theta. Theta is equal to pi over what? Theta is equal to pi over 3. Then theta is equal to pi over 3. And this will be the time unit, when. So this will be pi over 3 radians. So this is the radian unit. So now this is the complete setup. The complete setup is this right here. The complete setup is this right here. All the stuff in red. Yeah, I think I should have written this in a more organized way, but that will be the setup. Now once again, this setup 1 equation can be replaced by this other equation written in brown, right underneath it, if you like. So you take your pick. But note that in this case, the reason why the simpler equation, this setup, works is because we have an isosceles triangle. What happens instead of 4 and 4 here? Let's say the two sides are 4 and 5. If the two sides are 4 and 5, then this simpler setup does not apply. You must use the second equation. So it's not that this is useless. See, and when you look at the study advice I wrote down and the study advice I wrote down on the announcement, you always have to consider what could change on the problem. So here, the two sides are 4 and 4. But on the test, you might see 4 and 5. And and they'll be different. So if it's different, can you still use the triangle definition, the right triangle, to find the radius of L and theta? No, you can't. Then you have to now use this cosine. Okay? And now the question, why do you think the units must be radians? This is a hard question. Why should the units, why should the unit of angles be in radian units? Why should the angle, square bracket? I want the square bracket, not the fancy parentheses. Why should the units of angles be in radians? By the this is not an easy question, okay? It's hidden. You have to know the history of all the angles and all the where these formulas coming from. This is a hard question. Okay, must know how, why, must know. Anyway, this is must. Once if you want to all units, all differentiation formulas. Of trig functions or trig functions, assume trig functions, assume radians. Again, if you do not take derivative, then it could be radians or it could be radians. So let me write this down. The reason why we need these radian units is because we take derivatives. That's why. So if there's no derivative, then what? If no derivative of trig, then any unit of angles, then what? Then degrees or radians both ways. But the fact is that on this problem, we are in calculus, we will be taking derivatives. And that's why we need radians. Okay? The key point is that we take the derivative here. If we do not take the derivative, then we don't have to use radians. But as soon as we take derivative, we need to use radians. So why is that? Well, that's a hard question. So anyway, maybe I will ask you to figure out. Okay? So should I ask you as an extra question? Well, I don't know. Okay? But anyway, that's a tough question. It's not an easy question you can answer, but you have to know the entire history of, and so you have to know all the formulas of the derivative of trig functions, especially sine and cosine. Yeah, you have to know where the derivative of sine is coming from. Ultimately, the question is, where is the ultimate question is this? The question is, ultimately, the ultimate question, where is the derivative of sine, sine function, sine coming from derivative of f of x is equal to what? Is equal to sine x. Sine x from. Where is the derivative of where is the derivative formula of f of x to sine x from? It's related to this question. Okay? All right. Any questions here? So the question of converting these to radians, I'm not going to talk about this here because that is a question which will take me another, 15 minutes or so. But you have to kind of know where that is. If you're a good student, you want to be really good at this, then you should be, but this is not a simple answer. You have to trace it all the way back. And if you go all the way back, then you have to trace all the way back to that, what is it? Remember that formula? What formula did I cover during the week, or during day 1 or day 2? Arc length, the sector area formula? That's right. Do you remember the sector area formula? It traces all the way back to the sector area formulas. The sector area formulas are the formulas which will decide whether we should be using degrees or radians. That's the beauty of the competition between degrees and radians is the sector area formula. And so you have to trace it all the way back. Okay, but anyway, Anyway, in this case, if you're not curious, if you don't have curiosity, then don't bother. Just know that all the angles must be converted to radio units. Okay, that's all we need to know. Okay, so now, any questions here? Say save. Do you think you can do the rest of it or no? Save and then clear. Oh, sorry. Redo. There we go. So what I'll do is I'm going to what? I'm going to erase this part only. Let me just erase this part. Oops. Oh, what am I doing here? I don't want to erase these guys. Okay, there we go. Okay, so should I just do this? Okay, all right. You know, how about this? I'm not going to finish, but let me just start this. If you get the setup this way now, and how to solve it, this is how we solve it. Solve, and then the equation is going to be this right here. So that's going to be, we can write that down. Or you can actually write this. You can either keep it this way, or you can write L is equal to what? 8 times sine theta over 2. L is equal to, what is it? 8 times sine theta over 2. Okay? Now what do you do? How about you now apply differentiate both sides with respect to what? Theta. Or what is this? Can you do it? Differentiate both sides by theta. Okay? So by theta, it'll give us by theta. So if you do that, what you get? You get dl dt. dl dt equal to, then 8 is a constant product, so therefore 8 times the derivative of what? Sine theta over 2 with respect to t. So now, if you want to derive a differential sine of theta over 2 by theta first, we get cosine theta over 2. And now the derivative of theta over 2 with respect to theta, that will be half. So we need half here. And then now the single factor times d theta over dt. With this. Cosine theta is over here. And all you do is what? Is now substitute. Then substitute values. And the time condition also true. Time condition. And then you can get it. So in this case, what you have to plug in for theta? You have to plug in theta is equal to pi over 3. And then you have to substitute d theta dt is pi over 6. That's all you have to plug in. So all you have to do is plug in this value right here. Plug in the value of theta here. You have to plug in the value of theta. You have to plug in the value of theta here. And you have to plug in the value of d theta dt here. D theta dt. That's the d theta dt. So that's what you have to plug in. So what, let me just use green here. How about this? I have to plug in this theta and this d theta dt. Okay, what is d theta dt? That will be pi over 6. And a theta is pi over 3. Get it? Any questions here? You can try this for the second setup 2 equations. And then I think I have given you enough information to do part B as well. For part B, it's the area. So you have to use that area formula, okay, which I gave you already. Or cosine law, the area formula. Okay, so you can use that, and then get the answer. Okay. But you can also also what? You can also estimate this by your calculator. But now remember, when you use a calculator and you ask, and then you let's say check the area when theta is 135, and check the area when the angle is 136, and the difference is only 1 degree. But when you check the rate of area, then you know what? You cannot use radians. You have to use you cannot use degrees. You have to use radians. So in order to check your answer, okay? So watch out. So when the difference of degrees is 1 degree, then in radian units that will be pi over 180. So that would be a different number. Okay. All right. Any questions here? So there are some details you have to fill it in. So now what I'd like to do is I'm going to let this part be. I want to let you do this part B here. Okay. So now what I'm going to do is I'm going to save this and then we'll clear all this. Now let's look at number 5. I wanted to at least do exam 5 and 6 and 7, or there's quite a few more problems here. So I don't know. You know what? Maybe I cannot start chapter 3 today. Okay, so let's see. How about this? We still have time here. Okay, so maybe I'll just get the setup. Okay, does anybody have any questions? Questions on topics which is covered on today's test? Anybody has any questions on today's test? Are you all there?
Yes.
Okay. Any questions on anything? Nothing? Okay, then why don't we, the time is now 9:40 right now. 9:40, so why don't we just take a break then right now? I think it's a good time to take a break. And then after we come back from break, let me just continue with section 2.8. And then I'm not sure whether we'll have time to do section 3.1, but we'll see how things go, okay? So we'll see. Section 3.1 has a lot of definitions, a lot of terms. So I kind of wanted to go through those topics, okay? Because there's a bunch of terms. The first section in every chapter tends to have some terms, tends to have some new terms, because it is introducing a new chapter, and so they have terms in there. And so, but anyway, okay, so that's that. So let's just take a break then. So here, let's take a break. So we have a 10-minute break, 10-minute break, and continue as. Time is now 9:42. So let's meet at 9:52 a.m. All right? Okay, so let's have a 10-minute break. I will be back in 10 minutes. Good, let me just write midterm 2 today. Everyone must take 2. Start the test for 8 p.m. Right? We can start the test immediately. Okay, I'll be back in 10 minutes.